Hello, this is Dr. Hassan with Innovate, and this is lecture number 62, Reduction of State Tables using the Implication Table of Chapter 9, Design of Synchronous Sequential Networks, the course Digital Logic Design or Digital Systems or Digital Electronics. This is a disclaimer for you to read. I cite 3 references in digital logic design. However, there are many books in the area. In Chapter 9, we talked about the derivation of state graphs, we talked about practical applications, and we talked about the reduction of state tables using by inspection and by using the merger graph. We will continue really talk about the reduction of state tables by using the implication table, which is the third method of the reduction of state tables. Once we are done with the reduction of state tables, we will talk about state assignments, then implementations with and without VHDL. So the state table reduction techniques, as we said, by inspection, number 1, using the merger graph, number 2, using the implication table, which we will talk about it today, and the reduction of state tables using the partitioning method, which will be our topic in lecture number 63. Reduction of state tables using the implication table. The implication table, also known as the merger table or the pair chart, is based on the same principle used in the merger graph. However, the implication table is more convenient to use than the merger graph when dealing with finite state machines having a large number of states. So it's very convenient to use. Implication table used to check each pair of states for possible equivalence. Non-equivalent pairs are systematically eliminated until only equivalent pairs remain. Like the merger graph, the implication table can reduce state tables for both completely specified and incompletely specified finite state machines with minimal reductions. Guidelines. First, we have to construct the implication table, which contains a square of each pair of state. To accomplish this for n plus 1 states, with a state S0 to Sn, we will build a staircase table as shown. We have the column start with S1 to Sn, and the rows start with S0, S1, S2 to Sn minus 1. So by this, we will have a square for every pair of states in the table. S0 with S1, S0 with S2, and so on and so forth till S0 with Sn. Then we have S1 with S2, S1 with S3, till S1 with Sn. Okay, till Sn minus 1 with Sn, which is the last 2 states, okay, together. So by doing this, we will generate really a miniature square, a small square for every pair of states in the table. We will compare each pair of rows in the state table and perform the following. If the outputs associated with the state Si and Sj are conflicting, we'll place X because they are not compatible. If they are not compatible, they cannot be the same. So if Si and Sj are in conflicting output, they are different output, we place X in the Ij squared to indicate that Si is not equivalent to Sj. If the outputs and the next states are non-conflicting, or if the pair Si-Sj only implies itself, we place a check mark in the Ij squared to indicate an Si and Sj are equivalent. If the corresponding output of state Si and Sj for all possible input sequences are non-conflicting, but the next state, also known as successors or implied pair, are not the same, we place the implied pairs in ij squared. For example, if for the same input sequence, the next states for Si and Sj are Sm and Sn, Sm and Sn is the implied pair and will be placed in the square. We go through the implication table square by square. If ij squared contains the implied pair Sm Sn and the Mn squared contains X, then Si, or deleted, then Si is not equivalent to Sj. We place X in the ij square. If X or more is added in step 3, we'll repeat step 3 until no more X's are added. For each ij square that does not contain X, Si is equivalent to Sj. If the ij squared contains the implied pair Sm Sn and the Mn squared contains the implied pair Si Sj, then Si is equivalent to Sj and Sm is equivalent to Sn because we cannot delete them. So it's very similar to the merger graph, except this is more synchronized, more organized, and can handle a very large number of states without any problem. Let's take an example. We have a mode machine here, okay, and we have present state A, B, C, D, E, F, G. So we'll start fabricating, drawing the table. We start with B, C, D, E, F, G, and here we A, B, C, D, E, F. And by doing this, we will have really a square for every state. For A to be equivalent to B, we look at the successors. We have F here, so I'm fine with F, it's the same state, but B has to be equivalent with G. Okay, so this is, I will have BG. Now, so BG will be the successors. They have, we say A is equivalent to B if and only if B is equivalent to G. Now we do the same thing A and C. A and C, they have the same output 0, 0, so they could be equivalent, and to be equivalent, CF, the successors, they are CF and BG, CF and BG, CF and BG. Now A and D cannot be equivalent because they have different output, so we put X in the square, in the AD square. The same thing, A and E, they can be equivalent, and the successors EF and BD, EF and BD. A and F, on the other hand, A and F, okay, they have the same output, so we need AF, which is called implied pair, and BB. B is the same as B, and AF, so we put actually a tick. It means A is equivalent to F. So what we are saying, A is equivalent to F if A is equivalent to F. So we put tick. So this will be the first tick we have. A and G, they cannot be equivalent because they have what? Different outputs. So they have conflicting outputs and they cannot be equivalent, so we put X. The same thing with B. Now we start with B, B and C. B and C, we need F, C, or CF as the implied pair. C has to be equivalent to F. Okay. B and D, they are not equivalent, so we put X because they have different output. B and E, we need what? EF and DG. B and E, we need EF and DG. B and F, we need AF and BG. B and G, they have different output, so we put X. We start with C and D. C and D, they have different outputs, so we put X. C and E, they have the same output, so we need CE, this is implied, so we remove it, and we need GD or DG, so only we need DG. Okay, C and F, we need AC and BG, and C and G, we put X because they have different outputs. Okay, D, we start with D. Now D and E, they have different outputs, so we put X. D and F, we have different outputs, we put X. D and G, their successors, D and G, they have AF. D and G, they have AF and BB, which is the same, so we ignore it. So we have AF, so D and G. E, E, E and F, they have the same output, so we need AE and BD. AE and BD, the successors, they're implied pairs, and the successors, AE and BD. And E and G, they have different outputs, so we put X. F and G, they have different outputs, so we put X. So this is actually the first pass. So in the first pass, we filled out the implication table fully. So we study actually the second pass. Now, the second pass will depend on the first pass table that we just generated. Okay, for A to be equivalent to B, we need B to be equivalent to G. So we go to BG. BG, there is X, so we will put X here. So A cannot be equivalent to B, okay, because BG is cancelled out, so we will cancel A and B. So we put X in this square, and so on and so forth. So if we go actually, we establish the second pass and the third pass, okay, and you have enough literature I put for you here to read. Okay, so we end up with the implied table, with the implication table shown in the third pass. So we have so many cancellations. The only states they are not cancelled. A is F. We have ticks, so those are equivalent. A and F. Everything cancelled here. Everything cancelled here. D and G, they are equivalent because they are dependent on AF, and AF are equivalent. So G and D are equivalent. Anything else? So we end up, and this one, C and E. For C to be equivalent to E, we need D and G. D and G, we told them to be equivalent. So C and E are equivalent. So we have C and E, D and G, A and F. So three states can be eliminated. Three states can be eliminated. A is equivalent to F, C equivalent to E, and D equivalent to G. And the reduced table will look like the following. A, B, C, D, A, C, D, B, C, B, D, D, B, 0, 0, 0, 1. Now, we can verify that this is a final reduction. It is really the implication table give us a final reduction very nicely. But look at this. For A and B and C, there is possibility of equivalence here. For A to be equivalent to B, B has to be equivalent to D. But B has an output of 0 and D has an output of 1. So there is no way A equivalent to B. So A cannot be equivalent to B. The same thing with A and C. A and C, which is implied B and D. Again, B cannot be equivalent to D because they have different output. So A cannot be equivalent to C. B and C can be equivalent. They need A and C, and D. But we said A cannot be equivalent to C, so we ruled it out. So therefore, B cannot be equivalent to C. So this is the final reduced table by using the implication table. The implication table is a great method. Allow you to reduce any state table without any problem and with an optimal output that even you don't need to verify. But we verified this by inspection, and again, this will be the optimal reduced state table for this example. I thank you so much. This is the end of this lecture, which is lecture number 62, using the implication table to reduce finite state machine state tables. And By doing this, please subscribe by clicking on the blue circle. Again, I thank you very much. Hopefully to see you soon in the next lecture. Sincerely, Dr. Hassan.